Okay. Whoa, okay. All right, well, let's plow ahead. Okay, yeah, with physical optics, we start to look at light behaving like a wave. A little different look than what we did with the geometrical optics. It's introduced by Thomas Young, was the first one that kind of coming up with this. These are from his notebooks. He started talking about this. Different than Newton. Newton thought light was particle-like and had a whole different explanation. It's interesting, when we get done with this, it's looking like Thomas Young was all right and Newton was wrong. In the next section in modern physics, you'll say, well, wait a minute, there's a little more to this than meets the eye. So anyway, more on that later. Young was looking at primarily something like water waves as they would pass through a couple slits. You send water here, it's going to tend to spread out in a circular fashion as these waves travel through these little slits. And these two evolving circular paths tend to overlap, and they can, what we say, interfere. The idea that we can get, it's kind of hard for me to see up close here. Let's say something going out, this is creating a crest, and these crests are going off, these crests are going off, and we will get some points here where the crest of one wave is meeting the trough of the other wave, and they tend to cancel out along this line. These are called nodal lines. We'll call these minima. There's also parts where they're constructive interference. There'll be maxima, and there'll be a strong one in the center. Anyway, this is kind of how Young is thinking. Hopefully this makes visual sense to you. We're going to look at the double slit. We're going to bring in waves. In this case, it's going to be waves of light that are going to strike and open with a couple of openings here. Double slit interference is what's going to be set up. They have a distance d apart. These waves are going to go through, and they will start out in phase together. And then the question is, when they get out to some distant point on the screen, what are these waves doing? Are they constructive? Are they going together? Or are they out of phase and they're tending to cancel out? We're going to refer to this point on the screen as measured off at some angle theta out to that point. The screen is usually some distance L away, and the point is some distance y. We're going to be mostly dealing with small angles with this, so these distances, we'll look at this here in a moment. Now, since both of these start out in phase, a real important point is, how are they in phase when they get to this point? If we get to this point, we've got the same distance out here from this ray, and this ray will be traversing the same distance. And if these waves are in phase at this point, they will travel the rest of the distance and be in phase when we get out to the screen out here. If the waves are out of phase at this point, they will be out of phase when they get up here. So this, what we call the path difference, this lowercase del of the Greek alphabet, will be this path difference between this path and this path. Now, we're only going to be dealing with distances that are fairly great. As this gets bigger, these lines are going to become more and more parallel as they go out to a distant point on the screen. And these are going to be typically very small dimensions. This is going to be, del is this path difference, and it's going to be equal to d times the sine of theta. D is the distance between them. This point on the screen out here is at angle theta. That's going to imply that this is also angle theta. So that is that path difference. So this is going to tell the story of this. these are going to be interference maxima if in this space we have a whole number of waves. If we have a whole number of waves, that if they start out in phase and they get at this point and they still will be in phase as long as there's a whole number of waves in here. M is going to be just some integer. It can be plus or minus 0, 1, 2, 3. All the counting numbers, we're just counting up how many waves we can pack in that space. And we could solve maybe for this for some angle theta to get out where they hit on the screen. We will be using small angles for the most part. Sine is approximately equal to the tangent of theta, and that tangent of theta would be the side opposite y over the screen L. And so that's how we'll be determining the position on the screen that we have. Interference minima, where it's dark out there, if in this path difference we kick in an additional half a wave, that's going to throw them out of phase at this point, and they would remain out of phase when they get out to point P. So this is what we call destructive interference, where d sine theta is equal to m plus an additional 1/2 of a wave would throw them out of phase. And m takes the same role here. It takes an integer plus or minus 0, 1, 2, 3, and any of the counting numbers.
Don?
Yeah.
What happens if it's not, the path difference isn't like an easy wavelength?
Oh, okay, I'm gonna, that's coming. Okay, so these are just the easy ones. We haven't gotten to the difficult ones yet. Okay, let's do a simple problem using this. Something that kind of throws people, he has two colors of light are projected through two small slits. Now the light that was coming in here, we're kind of showing maybe just one light. Consider that we could have a bunch of different colors all passing, the waves, like water waves, just pass through one another. They would just come through here. So you can use if any number of wavelengths are coming through, as well as white light, which is composed of all the wavelengths. So don't be thrown by the idea that, wow, he's sending through two different colors. Maybe he's got two lasers, you know, a red one and a green one. He's going to shine it through the slits. And a screen is, okay, he's telling how far it is away. That's L from the slits. And in the first order, I didn't talk about this second here. Ooh, I guess I did it here. The idea that the order number, I should have put this on this other diagram. There'll be maxima and minima. This first one is m equal to 0. There's no path difference between this one and this one. And then there's going to be a maximum, will be m1. And between this first maximum and this maxima, there's going to be a minimum. Let me see if I can make some better sense of that. Let's see. Well, let me plow ahead and see if this is going to be bothering you. So I can say it's going to be d sine theta. Now the idea of sine theta is approximately, the tangent is approximately equal to y over L, so that's what I have here. He's saying this very first color, lambda 1, is landing out here on the screen 1.88 centimeters from the center. And the second color is going to, which is, so I'm calling one wavelength 1, is going to be a second color is going to be 0.37 centimeters further away. So its distance is 1.88 plus 0.37, and we're using the same screen. The m is the first order, so m can be, you know, all the numbers. So we've just got m equal to 1 for the first here, and that's going to be the first order. And then I can take these two expressions and divide them. I can take this one and divide it by this one. And you can kind of see how the math works. This is going to simplify. And this ratio will just be this number. Now we want to get what those two wavelengths are, because he wants to know what are the wavelengths of the two colors. So we have the ratio of the two, so that's one equation. I've got two unknowns. I also use the fact that he's telling me that the difference between the two, I've got lambda 2 is bigger than lambda 1. So I go lambda 2 minus lambda 1 is equal to this 100 nanometers. The two colors differ by 100 nanometers. And then we can go ahead and solve. We've got two equations, two unknowns. You can do that kind of thing. So probably the most confusion on this is people saying, well why two colors? I don't know what to do. I don't know what to do. You do them both, and you just compare the two. So that would be a kind of a simple example.
How do you know that the second color was up to the screen?
Oh, rather than down. Yeah, I don't know for sure. I was looking at that too. The wording on it was subtle enough that I would have gone up and asked him for clarification. When he says the second color is 0.37 from the first color. Good question. What if, is it beyond or is it on the inside? Take it away. And from what's worded there, I can't really say. It would give me a different answer. So yeah, I would say, hey, could you please explain this, or let me know what's going on. And I'm sure he would. He probably would then clarify that for the class. Okay, your question here. Okay, back here, let me go back a couple slides, back to here. A question here is, usually, for maxima, there's a whole number of waves, and for minima, there's an extra whole number plus a half a wave. What do we do if we're somewhere between these points, between a maxima and a minima? What if in here, when we look at how we put in waves, we have, maybe more or less than an integral number of waves? So here's how we want to look at this. As far as the projection on the screen, we get a strong central maximum, and then we get M1 on both sides. Sometimes we call this M1 plus and M1 minus, M2 plus, M2 minus. But if we're out here somewhere on the screen, we might be at some point between either a maxima and a minima. Then if you think about that path difference, again, being right in here, how many waves have I got? Have I got, let's say I've got a whole number plus a fraction. Let's say I've got 1, 2, 3, and not quite 4. So I've got a fraction here. Now this distance is this d sine theta, so I'm packing a certain number of waves in there. But now in order to do the math, I need to take these distances and turn them into radian measures so I can use my trig functions. Now a simple proportion will work nicely where we say this is the physical length of wavelength, the physical distance, and then this path difference is also a physical distance. But to use the trig functions, we need them in dimensionless radian measure. So I can do a simple proportion. I can say that lambda is to 2 pi as this del, or d sine theta, is to phi. This is going to be the phase difference between the two waves. It's not going to be a whole number or not a half. So again, this is this ratio. 2 pi is to lambda as phi is to del, the path difference. And of course we can arrange things a little bit. Usually we want to know what this phi is. What is the phase difference between these two waves? And again, just doing the obvious here. Now, in terms of doing problems, we used this trig identity earlier in the course, in the first section when we first introduced waves. How we would take and add two waves, and we'd end up with either the sums or the differences of these terms that are inside. So using this, we can come up with an expression for the electric field at some arbitrary point on the screen. The idea that we've got one wave is going with some angular frequency, omega t, plus that same omega t plus this phase difference for the other wave. And we want to come up with what these two are. Here we can use the trig identity to get the differences between these two. The difference is just phi over 2. That's the differences. And then the pluses, when we add the two together, we're going to get a 2 omega t, but we're going to be dividing by 2. And so we end up with omega t plus phi over 2. And so this is the more complicated expression for when you are out at some point. We can go ahead and put in for phi, and actually, yeah, okay, okay, so we've got this. Now, what we're going to do is we want to get the intensity of this. Now, earlier in the course, we dealt with most waves. The amplitude, the power, the intensity was proportional to the square of the amplitude. In the case of light, this is the electric field, and the idea that the intensity should be proportional to the square of the electric field. And so here's where I can take this whole expression for this electric field. Let me do this part of it. And I'm going to do a time average. So I first want to square the whole thing. So I'm going to end up squaring all these terms. But I also want to use the idea that this is the average intensity. This sine omega t just means it's vibrating very, very quickly, millions of billions of times a second, very, very high frequencies. In the time averaging of that, it looks like it's such a blur to us that we will just deal with the intensity as being one factor, not time varying. And then over a whole cycle, this term is going to average to the factor of 1/2. So the stuff as far as you remembering this is going to be that I max should be equal to the maximum I is, that would be the maximum intensity here, all times the cosine of phi over 2. And for phi, of course, we can put back in, that was d sine theta. So this will be an expression for wherever we're at on the screen. So if I'm out here at some d sine theta, I can come up and get the amplitude and square it and come up with the actual intensity of the light at that point. And so all across this whole scan, we can deal with not only just the maxima and the minima, but any point in between. Wow. We got a lot of stuff here, and if you're in a point where like you're behind, I would say likely he isn't going to use this, but he has. So I wouldn't. Anyway, if you play the odds, you might want to say, hey, don't worry about it. Or if you do want to worry about it, you just need to cram this in your head if you didn't follow what I said here. This idea, though, of this turning this path difference into a phase difference is an important idea, and that part of it is actually not hard to get your head around once you set your mind to it. Hopefully. Okay, now I'm moving to diffraction gratings up a bit here. In the book, they saved it for the diffraction chapter, since, oh, these are diffraction gratings. Let's talk about it. Now, the book had a little disclaimer, too, said it was probably better to describe a diffraction grating as an interference grating. What we're going to do is we're going to take a double slit interference, which hopefully we've got a pretty good handle on now, where we have 2 slits. And then what if we have 3 slits? 4 slits, or 5 slits, or 10 slits, or in the case of a diffraction grating, you can have 100,000 slits. Okay? What happens is, I wish I could explain this better. Earlier in the course, in the past, the book covered something called phasers, where we can actually take and develop these patterns, and as well as some other things with diffraction. And they cut it out, probably wisely, because there's enough to deal with. But the results, you're just going to have to kind of take and maybe believe. The idea that the position of the screen out here, where we have our our main maxima. As we add slits, we're going to have maxima, let's say at here with 4, we're going to have a maximum that is going to get sharper and more well-defined with a greater number of slits. It turns out there's some little secondary maxima that are really pretty tiny, and as we add slits, they get tinier and tinier and negligible. What you want to keep in mind that the principal maxima for anything with let's say a large number, this has just got 10, these are going to be occurring at exactly the same position on the screen as the would for a single slit. This is the basic idea behind a diffraction grating, and why I want to introduce it here is that essentially you can get the peaks of the diffraction grating by just using the equation for the double slit. The primary maxima are the same for the two. And so the idea of d sine theta is equal to m lambda, where m again can take on the value of 0, 1, 2, 3, 4, and so on, that will describe where the positions of the maxima are in terms of like the angle out on the screen or out into space. And they typically will give you the number of slits that the diffraction grating have and the width of the slits, the diffraction grating. So to get the distance between the slits, you just take the width of the grating divided by how many slits you've got, maybe 100,000. And then that would give you a tiny distance between them. And for a diffraction grating, this d is usually something very, very small. One word of caution, with the double slit, we were primarily dealing with small angles. It's small on the screen. With the diffraction grating, because they're so tight, they can spread out quite a bit. And so the angle, we don't want to use small angle approximation. Do not assume that. So don't go y over L here. Keep it sine theta. But then in terms of a problem you could solve for theta is the angle something's going to go off at. Okay, so if we look at, this is kind of a case like we had a little earlier, where what if we have two colors and we put them through the diffraction grating? Now what happens, always in the center, this is where they all travel the same distance. There's always a maximum right in the center of this thing. And then there's going to be m values. There's m equal to 1 is off here, and you could say this is -1, or this picture just uses 1, and that's fine. The first order is on either side of this principal maximum, and then there's m2 terms which are on the outside. So you go principal 0, then m1, m2, and it goes on m3. And we can project any number of waves. So this first one, if you watch this, we get like a red and a blue light. The blue light is a shorter wavelength, so it goes from a maximum here to another maximum rather quickly. That happens there. The red gets pushed back. It's a longer wavelength, and so it goes a little further back. And then it's going to repeat again for M2. So the blue of the M2 is here, and then the red is out here. So these are M2, these are M1, and again M1, M2 on either side. We can send any number of waves through there. For instance, white light. If we send white light through there, we get a whole rainbow here at M1, because they're all different wavelengths. The blue lines up here, the red over here, and then we get out here, and what happens with the higher order terms, they tend to spread out more and get a little more, and they're also quite a bit fainter. They're not as easy to see, but they are handy in that they get broader here, so you can sometimes resolve things that you can't resolve things with m equal to 1. But you do want to have this idea that M1 has a whole rainbow associated with it. M2 has a whole rainbow. M3 has a whole rainbow. And sometimes we need to deal with something like, let me give you kind of a problem for that, is a diffraction grating. This is one that gets used on tests here. What if the wavelengths of the visible spectrum, that's between 400 and 700 nanometers. 400 is the short wave, so this is the violet side or the blue side, and then the longer is reddish. And he wants to know what wavelengths of the visible spectrum overlap between the second and the third order. So again, this first order and the second order stay relatively well defined. When we get out one more, M3, it gets spread out a little more and they start to overlap with M2. Okay, so, in the third order, this would be between the second and the third order, so that's M equal to 3. We have d sine theta is equal to m equal to 3 times the wavelength. Now, the one that's closest in is going to be that violet. Blue, violet's closer in than red. Red's further out. So let's start with violet and see where that from the third order overlaps with the second order. Now, we should be talking about some point on the screen, and that point on the screen can be defined by d sine theta. So in the second order, this part doesn't change. We're talking about the same point on the screen where they're going to overlap, so their thetas are the same. We're using the same slits, and so that would cancel. And then that for the second order, and we want to find out what this wavelength is. That's that color. Okay, so again, since these two things are equal, we can go ahead and set them equal. 3 times 400 is equal to 2 times lambda, just setting these two things equal. And I can come up with a lambda of 600 nanometers. That's where, the violet would start to overlap with the red. That would be that first overlap. Then we also have the second order. The second order red, since it's the furthest out, this red is out here, the second order red is out here, it's starting to go out and mix with the third order. So using second order red at 700 nanometers, second order, m equal to 2 times the wavelength 700 nanometers has got to be equal to the third order times that wavelength, or whatever that wavelength is. And then we can solve for that, and that's around 467, so that's kind of blue or violet. Just kind of these color things are just kind of qualitative. You primarily want to know of the visible spectrum between 400 and 700 nanometers. So the third order violet overlaps with the second order red, and this red overlaps with the third order violet. Okay. Didn't say that well. Yes?
If you tried to say that the red light of the third order was overlapping some light of the second order, you would get something that's ultraviolet?
I think...
You get some wavelength that's ultraviolet?
Oh.
You could say that that's just...
I think you'll find that where you're going to get, I think you'll get an error. It's going to tell you. So you could make that assumption, and I think you will not be. I think since you're setting a d sine theta, theta can't be.
Like for the second order, if you're looking at the third order red, the second order light would be ultraviolet.
Oh, I see what you're saying. Yes.
So you would come out with a wavelength that's ultraviolet, so you know that that's not.
Okay, right. You'd have to do that. Yeah, clearly. The light we set through here could be all kinds of light. This is white visible, and this is that rainbow. If you start to incorporate ultraviolet, it's back. That extends back here. It's a kind of a bigger rainbow, or infrared is back this way. And so, if we started playing it that way, we'd have to know something about their wavelengths. But we could do it. Yeah. Okay, so this is kind of a hard one, but anyway, if you can kind of get your head around this, I think has a lot of ideas in here. You'll understand this stuff about the diffraction grating. And again, do not assume small angles. Always play with this d sine theta is equal to m lambda. Again, the idea of the distance between them. Other than that, this pattern is going to look very much like it does with a double slit. And if he does something like take a double slit and put a white light in it, it's going to also form these M's. They're going to be a little broader, and they will tend to be more overlap. But this basic pattern works for any number of slits, 2 through however many that you have. Okay, so again, it's probably better termed in interference grading. Okay, got thin film interference. Okay, that's the colors in oil or a soap film, soap bubble. And the basic idea of this is we introduced earlier in the first part of the course the idea of phase change on reflection. The idea that you could send, this is just a rope of course, a pulse towards a wall or something. This pulse, when it gets there, it wants to jerk up on the wall, but it's tied to the wall, so it doesn't. So the action is up, but the reaction is down, and what's going to happen is that this reflected pulse is going to be upside down from the original pulse that's coming in. We would say this is phase inverted or out of phase with what it was with when it was coming in. Another thing is we could have a loose loop here where an incident pulse comes here. It jerks up. There's nothing to resist it, so that upward jerk just gets sending the wave back out in the same direction. So there is no phase change on reflection. So we're going to use these ideas. Of course, we're talking about light and not glass. And okay, so if we deal with something like light coming in, and so let's going from, let's say, a low index of refraction to something that has a high index of refraction. We send in this light pulse, and it would hit here. It would act like a bit like this fixed wall, where we're going to reflect this wave, and it's going to be inverted. So it's going to be it's inverted from its original direction, and that would be the transmitted pulse. Then if we're going from a case of high index to low index, we send this pulse, it's going to go through. When that pulse gets here, there's very little resistance. It's going to act like this loose element that is going to allow this pulse to move out. So this reflected pulse and the transmitted pulse, we say, are going to be in phase. Okay, so we're going to use these basic ideas when we get to, I'll start off with kind of an oil film on water. It has to be kind of a thin film for ordinary light that we have here. The light has to be of a short or coherence length. It's really only going to happen with thin films. For thicker things, it can work for something like laser light, where you can have a longer coherence length. But anyway, this is a lot of arm waving to insist that this thickness has to be small in order for us to see this effect. Now, this would represent the air up here. We've got the oil and the water here. The light coming in here. All of the things we're going to be dealing with, the light is really going to be coming straight on in, because if we come at an angle, we could do this, but we've got enough to deal with. We come in, it's going to refract a little bit and go back off. Consider that all of this, I'm kind of angling it out there just to help us sort out what's happening here. It is coming straight in. So this light is coming in. One thing it's going to do, some of it's going to reflect. It's going from a low index to a high index, so there's going to be, let's say, this phase change. And I'm going to circle this ray as being phase shifted. In the past, I put the circle here, and I think Dr. Young does that too. But this phase shift is for the reflected wave. One thing that happens on all of these things when they're transmitted, they're always transmitted in phase. So there's no phase shift on this one, but there is on the reflected one. This one will come through. Actually, I don't have, it also transmits, but it also reflects. Here I'm going from a low index, from 1.5, almost 1.5 to water, 1.33, so I'm going from a higher index to a lower index. So on this reflection, there is no phase shift on this other ray. So now this goes on and on. We could deal with reflections back and forth of some of these transmitted, some of these reflected. Let's primarily just look at these first two are going to tell us the story. These two are this is phase shifted, this is not phase shift. We have one phase shift between these two. Now, imagine first when you're thinking of this, think of this thickness here as being negligible, very, very small. And just look at these phase shifts. Now, the fact that this is phase shifted between these two, that's going to knock them out of phase. This indicates destructive interference. So again, the first reflected ray has one phase shift. Two rays will be out of phase, resulting in destructive interference. Okay. Then after you determine that, then say, well, we could have some thickness here, and this destructive interference will remain the case as long as I have a whole number of waves here and back. I will still be in the same position of having destructive interference. So the idea of the wave coming down and back is a thickness of 2 times t, there and back, has to equal to a m times the number of wavelengths, but it has to be the number of waves that are in the material, the medium. If we go ahead and realize from earlier that the wavelength in the medium is the wavelength in free space over n, the index of refraction, I can put that in here and take the n over here. So usually you'll see in the book, they keep writing 2nt is equal to m lambda naught. This is sometimes called the optical path length. But it did just come from this idea. We were traveling the distance 2t, and they were dealing with a shorter wavelength in the material, or more conveniently, we do it in terms of its wavelength in free space. So we will have destructive interference as long as we have a whole number of waves in that thickness. So that whole number of waves can be 0, 1, 2, 3, and so on. If we want to get constructive interference, what we need to do is in this path here and there, back 2nt, or 2nt, we need to have a whole number plus at least 1/2 of a wave more, and then we're going to have constructive interference. Now, these roles, these equations, don't just write the equation. You have to think about first what's going on with this. In one case, what is destructive in one will be constructive in another case, and vice versa. So we need to be careful with that. And you want to reason it out on this idea of phase shifts. Okay, let's see. Okay, we'll deal with some optical coatings. Here's let's do another one. Let's deal with both the reflected light and the transmitted light. So like an optical coating, typically your lens is made out of glass, and you want a thin layer of material placed on the outside. Maybe you want to cut down on reflected light for this thing, and that's going to improve your transmission, as you'll see. If we do something like this, I bring the incident out here, it hits here, it's going from a low index to a higher index. So there's going to be a phase shift on this reflected ray. So I got a circle indicating that. And then it's always transmitted in phase. So coming in, it goes in phase out to here, and then it's going to reflect off. But it's going to reflect off here. This is 1.38, this is 1.5, so this is a higher index. There's going to be another phase shift on this one, and it's going to go on through, and it will transmit as well as reflect. This reflection will not have a phase shift, but anyway, this goes on and on. I'll let that be. But let's look at the reflected light. The reflected light is the connection of these two. So I've got a phase shift here and a phase shift there. With two phase shifts, that throws it back into phase. So that would mean that this would be a case of constructive interference. Again, just to kind of picture these thicknesses very small. And then it will remain constructive interference if in that path difference 2nt is equal to a whole number of waves with that, and that n is the index of refraction of the coating. And that will be a condition of constructive interference. Destructive interference would happen in the case where we would have a whole number plus an additional half. Would take these two that have destructive interference, kick one by a half a wave is going to put them back into phase. Did I say that wrong? This is destructive interference, this is constructive interference. Now, for transmitted light, take a look at this. This has come in. Of course, the reflected light was phase changed, but the transmitted light is never phase shifted when it comes through. It transmits through, and it will go through this medium and travel right straight through with no phase shift. Then we have this one reflects off, and it's going to reflect here. No phase shift on this reflection, so there's one on this side. So between these two waves, where there's nothing here, there's one phase shift here, we've got one phase shifted. And so for the transmitted light, we have one phase shift. That implies that it's destructive interference. So if in this distance, 2nt, we have a whole number of waves, this would be destructive this way. Constructive interference would occur if we could kick in an additional half a wave in that path difference, and that would be the 2nt. So you'll notice between these two, for transmitted, this is constructive, whereas for the reflected light, this was destructive, the same formula. But they're opposite effects, which makes some sense. If the light gets through this way, it clearly didn't come back this way. Also on this one, this is constructive this way, where light coming out constructively out this way is the same as for destructive interference for the transmitted light. So again, they're going to be opposite. So the idea of which one is it? Is it this or that or that? You want to stop with this and start with these idea of phase changes on reflection to know which pattern you're going to be looking at. Okay, got some homework problems and a number of problems they've got in the book on thin films. One that's a classic one, and this is from a test question, is you've got a couple slides here made out of glass, and you've got a hair stuck in there, or small diameter wire. Okay, when it's illuminated with sodium light from, and it would be illuminated from above, it says there are 33 dark fringes. Okay, and it goes on to do another part of this, but let's just look at that idea that as we go across here, we shine this light in, there's differing thicknesses that we have across this thing. It starts out at very zero thickness, all the way up to the thickness of that wire. And we're going to start to get some banding of colors. In fact, it's very similar to the soap bubble. This was made, you make the soap bubble and you just hold it vertically. The water tends to run down, and where it runs down, it piles up here, it gets thicker. And up here, it's real thin. And you get this banding effect. We're going to get a banding effect across here that we're going to see. Dr. Young, I believe, showed you this one in class, where you use a sodium lamp with a couple, we call them optical flats, to get some really nice effects. But we have this idea that we have this thickness in there that could, there could be constructive or destructive interference. And it's going to be an alternating between destructive, constructive, destructive, constructive as we get this thing. Now, one thing that he's going to ask at the edge where the two plates meet, is it a dark or a bright fringe? And this is, what is it when it's here? I'm bringing this in, a picture from the book, that using the same thing, thin films would be this space between these. I'm not going to do this problem, but the idea they touch here, and you'll notice where they touch is actually a dark fringe. And we can look at why that might be. Let's consider that, and let's take a closer look at what's happening here. We've got these two glass plates, and consider that these are very, very thick compared to our thin air layer, and that's just air inside here. Typical case, the light is coming in, it's going to reflect off this first surface. Now notice I left that, a lot of students say, well, what about up here coming off of this surface? And next, all of that is going on, but we will not get clear interference except for very thin films, and so this is where I'm focusing. The light somehow comes through here, it's going to reflect here where there should be no phase shift. I'm going from a higher to a lower. Then there's going to be transmitted in phase, it's going to be reflected off another piece of glass. Here there should be a phase shift. So between these two rays I've got a phase shift, so that's destructive. Destructive interference, one phase shift. And as long as in this space, and this can repeat, as long as in this space 2nt, the thickness of that, is equal to a whole number of waves, we'll have destructive interference. So this is where it repeats as it gets thicker and thicker and thicker. We start off really at the point of contact is really where we'll call that is m equal to 0. Then that's the first dark fringe, and then we'll have a m equal to 1, 2, 3, 4, and we'll just use different m's till we get all the way out to the thing that we're going to be measuring. So he's suggesting here when it's illuminated with sodium light, there are 33 dark fringes. So we need to count 33. Now, he's checking to see whether you know that, we count the first one is at the point of contact. That is m equal to 0. So when I count, I have to count 0, 1, 2, and then we're going to go up. We're going to count up to actually include 32. We wouldn't use the 33 because I've already counted the first touching point as 1. Okay, these are things that hang people up. So if I want to get this, what is the diameter of the wire? Okay, he's got two questions here. What is the diameter of the wire? So we come up here, the diameter of the wire, that'll be the thickness. And so it's going to travel that thickness to n, and n is just 1 times the thickness, is equal to m lambda, where m is going to be 32, so that we have 33 dark fringes. And then I can get the thickness of that wire, and I've got that at 9.42 nanometers, so this is pretty small. Where the plates meet is dark, and again, probably the best visual evidence I can give you is this idea where they do touch will be a dark spot. Then he has you, he's not done with you yet, and what is the index of refraction of the fluid? Oh, excuse me, when the experiment is repeated, submerged under a fluid. So we went from air along with a fluid. With a fluid, there will be only one phase shift. Now, the idea that this fluid, I don't know what the index of refraction is. We're supposed to find that. Is it higher or lower than 1.5? Maybe it's less. If it's less, then this stays the picture. If that fluid is got an index of refraction that's greater than 1.5, then we will still just have one phase shift, but it will be the top one that's phase shift and the bottom one won't be. Still, there'll be one phase shift. It doesn't matter. So you're still a case of destructive interference. You will use 2nt, but now that's going to be 45 wavelengths. Since it went to 46 dark fringes, so again we count 0 up to 45 times that wavelength of that light, and then we can get the index of refraction of the material. So some examples of these things. Once you kind of catch on to them, they're actually fairly simple, but at first it's all kind of going on as kind of like a movie, and it's difficult to sort of sort it out. Okay, how are we doing? Okay, another application. We've got all these applications. Is the idea of the Michelson Interferometer. The idea, you used this in the lab this last week, so hopefully it's fairly fresh. The idea, you take maybe the laser light, you shine it in through a half-silvered surface. We build two paths. One is going to travel through, reflect off a mirror, and reflect ultimately back to the screen or the observer. The other ray is going to come in and reflect up off this mirror, and it's going to come down. And these two waves are going to interfere with one another, either constructively or destructively. It has to do with the difference in path between this one and this one. Anyway, you kind of saw the bullseye pattern between destructive, where we would have 0, and constructive, where we have a bright spot. Okay, typical problems on this. The idea of the interferometer, what really matters is going to be the path difference. So we're coming back to that idea. This part is in common with what we've had. There's one path that's different here, that it goes up, and this one comes over here. So these two paths could be different lengths. What's going to be important, what is the path difference between them? The path difference of an interferometer is moved through, okay, this is 88.4 micrometers, and so this is a very slight movement you used a mirror that moves, a movable mirror that moves back, and it has 300 bright dark fringes, and are counted. What is the wavelength of the light that is used? So the idea that the path difference is going to travel through some distance that the mirror is going to change. This is where we really want to get at that path difference. We start out with them the same. We're going to change one. And as we do that, the distance down and back, because the light travels two ways through that distance, that's going to be 2 times that distance, is going to be equal to the number of waves times the wavelength. And here we had 300 bright dark fringes, so they were alternating 300 times. We can then go ahead and solve for the wavelength. So the math on these is fairly simple. Trying to get your head around the concept is where you really need to focus. And then once you have that, the ideas of these are fairly simple. Okay, we did another one, and I guess we did it in the Friday lab, where we got the index of refraction of air. But it's my understanding Dr. Young cut that on the lab. Did anybody do that in the other labs? Okay, so maybe in the interest of time, I'll skip this one, since I think he won't do it. Or do you want me to do it anyway? There is a homework problem related to this. Skip it? Okay. Okay, we see. Okay, we do have a lot of ground yet. So, okay, single slit diffraction. This idea. We're going to take light and we're going to send it through a slit, and what's happening is there's going to be some interference taking place. We're going to have a bunch of point radiators, an infinite number is the way we're going to look at this. And let's see, a couple ideas we need to develop. This is fairly simple, the idea of Huygens principle, the idea of an expanding wavefront. If you've got some kind of wave, that each point on that expanding wavefront is acting like a very new radiator, a point radiator, and collectively they're all going to build the shape of this wave. So this idea is a very powerful one in terms of creating various shaped waves. If it's a plane wave, the plane wave is moving along, and each of these points is radiating its in a circular fashion outward, and collectively they would remain a plane wave. This is the idea of Huygens principle. Now the single slit diffraction is we're going to bring the light in, and we're going to consider that this whole slit is an infinite number of little point radiators that are all infinitesimally adding to the wave. Okay, and it sounds like this could get really messy, and it could, except we're going to deal with just the idea of finding the diffraction minima, so just a very special case. If we take and divide this slit up into two parts, even number, and we take something like this, well, actually we can pick any one of these. Let me pick this point and this point. When this light wave hits here, these two are going to start out in phase. They will remain in phase as we go out to the screen as long as we've, I gotta be careful. I want a destructive interference. I'll show you the difference here in a minute. Between this radiator and this one, or excuse me, this radiator and this one, if they are a half a wave out of phase, meaning that in this distance, which is A over 2 times the sine of this angle, is a half a wave. So if I've got a half a wave here, they will give me destructive interference as I go out to the screen, and it's going to be a dark spot out there. So again, if these two if these two are out of phase, then A2 over 2 times that distance times the sine of this angle theta, instead of d sine theta, this is A over 2 sine theta, is equal to a half a wave. I'll get to some more here in a minute, but this is the basic one for the very first minima. And then if we take the same, now the idea is if these two are going to be out of phase and they're going to cancel, we drop down to the next two. Then these are the same distance. These two will be out of phase and cancel. Drop to this one. These two are out of phase and cancel. Drop these two. These two are out of phase and they cancel. And we end up canceling all of them. So I'm just looking at what I can do for between two of them, and then I'm extrapolating what's going to happen to all of them. So this, again, is the case is if for a half a slit, this is a half a wave, I get destructive interference. Now you can continue to do this to divide this thing into an equal number of parts. So I go from 2 halves to 4 halves. So 4 halves of this thing. If I pack in a half a wave in here, I'm going to get another destructive interference at some angle between these two. And if I have these two canceling, then the next two cancel, and the next two cancel, and next, and next, and next. So I can play with that idea. So that's A over 4, dividing that thing into 4 parts is equal to a half a wave. If we want to take in general and divide the slit into 2m equal parts, okay, diffraction minima will occur for every A over 2m instead of 2, 4. This is going to be some even number, so that's going to be 6 and 8 and so on. That has to equal a half a wave. Now, usually we'll get rid of these 2's and we express this here as m sine theta is equal to m lambda. And this is the general expression for dark diffraction fringes going through. One thing you want to take a look at when we divided this idea that 2 over m, if I'm going to divide this slit up into whole numbers of parts, m can't be 0. When dividing by 0, that wouldn't be allowed. So unlike interference, we do not count m equal to 0. We just count the whole numbers, 1, 2, 3, and so on. And that would represent this diffraction this diffraction term. But note that these are not maxima, these are minima that we're looking at. And let me just go back to that picture here for a second. The idea that we're going out at a certain angle, there'll be this first one. This is m equal to 1. There'll be another one, m equal to 2, m equal to 3, and so on. But these do locate the minima, not the maxima. You have some homework problems, and sometimes the author will do a shortcut. Well, where are the maxima? Well, they're not strictly halfway between these two, and so it's really not proper to say that you'll find the maxima at a sine theta is equal to m plus a half. You will see that, and they do that in the book. They don't explain it. That's implying merely that the maxima are halfway between the minima, and that's actually not the case. They're actually a little more into the center. And so, but this is precise. This will tell you where the minima occur. And that's all we're going to really do with the diffraction at this point. Single slit diffraction. Okay, now where we can put this all together? And what if we've got two, in fact, here's kind of the construction of it. Let's say we're going to do a double slit, and each of those slits is not a point source. In the first part we looked at, these were effectively little point radiators, so the width of this slit is very, very small. There's also going to be a distance between the two. So that's the d. So with the interference, you will have the d sine theta. When we're dealing with the width of the slit, we're going to be dealing with an a sine theta for minima. Okay, and now there's some things that they don't derive in the book. Earlier we took a look at this. They used to, but they just really give you this as an expression for this overall pattern for light hitting these two things. Now, what you want to look at is when you're taking a look at this, I'm going to group this over here. This is actually the amplitude for the interference pattern. Let's get more to a visual orientation on this. Normally, we get the interference pattern is going to go across the screen, and you'll notice that the brightness of these is varying. The interference pattern, when we see it, it's usually brightest into the center, and it falls off pretty rapidly on either side. And what that is due to this diffraction that's taking place. Earlier, when we just dealt with 2 point sources, the idea that they would interfere out on the screen, anywhere out on the screen, they're going to be equal in magnitude in all directions. This isn't the case because we really have to have some width to the slit. So this red line would represent the interference taking place. And what's happening here is that interference is being modulated or enveloped, that's blue dotted line, by this expression. Imax would represent the very largest maximum amplitude. That would be a central max. And then its brightness is modulated by this diffraction term, or this diffraction envelope. Think about this. As far as the light coming through, it comes through the 2 slits, and they will interfere. But through those 2 slits, where it gets dark, that is at a minimum. So even though that we had a line here, you can maybe see it very subtly here, it's not bright, not because it's not constructive interference, but because there's this diffraction minima. Basically, there's no light because there's no light sent in that direction. So that cancels that out. And we get another one over here, and every place we have m equal the destructive interference taking place on due to diffraction, that is canceling out what we're getting with constructive interference. So hopefully that makes some sense. I know people kind of struggle with this. This term, this blue dotted line, this indicates the maximum brightness that it could have. And then inside this we have the interference pattern, and it is, the amplitude of these is controlled by the amplitude of the diffraction pattern. So hopefully these pictures can help you kind of see what's going on. Using these two ideas, case of the missing fringe, here I'm kind of talking about how this gets dark. We can look at this now, that the idea that we would have had a fringe here, so that is constructive interference for double slit maximum. D sine theta is equal to m lambda. I've added a subscript here, I, for the interference part, because that can take on the value 0, 1, 2, 3, and so on. We also have the minima are going to locate A sine theta is equal to md lambda. M is the integer, but this is for diffraction. So again, I can't use 0, but I can use 1, 2, 3. These don't have to be the same number. They just need to be a whole number. And the idea that I would have some interference pattern here, so I would have constructive interference for one of these, and then I would have destructive interference from the single slit diffraction. So these two in a sense are going to kind of cancel out. So if I take these two and I divide by one another, we would be talking about the same point on the screen, so the sine theta is the same. And I'm realizing here that this very first one for the diffraction, that is m diffraction, would be the value 1. M of the interference, I've got to pick that out, but this should be related to the ratio of these distances. We have the d, the distance between them, over the actual slit width. In this particular picture, I see that my very first diffraction minima, A1, or M sub D1, and then the interference here, this one, let's see, let me see if I can count. It might be easier to count on this one. This is the central. So this is M1, M2, M3, M4, M5. And it looks like we're missing M6. So the M sub I is going to be 6. And the A is 1. It's going to repeat again. Your second one here is going to happen when you're over 12 fringes. So these are the case of the missing fringes. And so when I look at this, just this picture, I can't tell exactly what A and D are, but I can tell what the ratio is between these two diagrams. Okay, so hopefully you can see that. Maybe as you revisit the notes, I got those online. You can, Dr. Young sent you a link, I trust, and you can take a closer look at these. So these are typical exam type questions that, if you really get the ideas, they actually are fairly simple, as is most all of this stuff here. Okay, we've got a couple topics here. These are fairly simple. The idea of a circular aperture. Instead of using a slit, we can use a circle, and we can shine like a laser light through it, and it's going to form a pattern out on the screen that's going to look like this. And this is a diffraction pattern. It mimics this single slit diffraction. Here we've got, instead of for single slit, we'd say it's going to be a small angle. So A sine theta, or the minimum, is going to be equal to M1. This is for M equal to 1, lambda over A. So this is kind of how we would play the game for a single slit. We do it almost the same for a circular aperture. Instead of a 1, however, if you do the math, and we're not going to do the math, we're going to find that the first minimum occurs not m equal to 1, but m equal to like 1.22. This has to do, you have to integrate over the circular cross-section using Bessel functions, and it's all fun, but you get a simple answer. So we're going to use that simple answer and just accept it. So that theta minimum would mean that if we're out here on the screen, theta minimum is going to be the angle between these two rays. One, the central maximum, which is always bright, and then there's going to be the first minimum, and that's what we're going to focus on. This is going to tell you this tiny little angle that we have between those. And d is going to be the diameter, not the width of the slit, but is going to be the diameter of that aperture. Okay, so how do we use this? Typically, we're going to use it for the case of resolution. If we have a couple of different sources, this source can have its diffraction pattern over here. This source can have its diffraction over here, and they don't they overlap a little bit, but they're pretty well separated. As we bring them closer together, we're going to get these patterns more and more on top of one another. And so it's going to look more like this. And in fact, what's going to be key for us is that if we separate these things, we're going to get these two patterns on the screen, one due to one opening and the other opening. Here we'd say these are separate enough we can say we can resolve these. I can see that there's two spots of light. As we bring them closer together, they start to overlap a little bit, and this might look suspicious. It might be just some bad optics. I suspect that first. And I don't really know if there's two dots of light there or just one that's just kind of weird. If they do get close enough together, we tend to overlap these patterns. It looks like there's really just one source, where there actually could be two sources there. So this is a case where we say we don't resolve it. We clearly resolve it here, and right on the borderline is what's called Raleigh's criterion, is where we get them close enough so that the maximum of one sits right over the minimum of the other one. And this one's maximum sits over the minimum of that one. And so that is the case of what we'll call Raleigh's criterion. If he asks about minimum resolution, and he does have some problems relating to that. One of these, it's been said that a top-of-the-line spy satellite can read the letters on a package of cigarettes 250 kilometers above the surface. Assuming the letters are 3 centimeters, these are big letters, tall, what is the minimum lens diameter on the satellite that he can actually resolve these? So you want to think, I'm thinking of the satellite, it's probably got probably a mirror, but we could use a lens here just for simple construction. Use some kind of lens where we're looking at that distant L, and we want to see if we can actually get that pattern here. So consider that I've got a point of light up here. It's going to pass through, and it would pass right through the center of that lens and would land over on this spot. The other side here, the bottom of this L, is going to go, I guess I've got it on the axis here, so it's just going to go straight on through. I've got the two of these things, and I'm going to be able to, we say, resolve these as long as they follow Raleigh's criterion, that the minimum angle between them is 1.2 times the wavelength over the diameter of the opening. Now, this actually is pretty simple if you think about it. This determines how accurately you can resolve things, that minimum, depending only on the wavelength of light you use and your diameter you're opening. And then as far as the stuff that's out here, this can be a long way away, and these could be fairly sizable distances between these. These could be two stars and 2 points of light, 2 headlights. Here they're just 2 points, top and bottom of the letter. And if you look at this green line that comes straight through the center here, and the red line comes straight through the center, there's going to be this angle here is the physical angle that we're looking at this letter. This, again, tends to be, I mean, this is 250 kilometers away. So this is going to be a small angle also. So all of this stuff we can probably use small angle approximations. But one thing we can look at this theta, and clearly we can say, oh, well, it's pretty simple. The tangent of this theta is 3 centimeters all over 250 kilometers. And here, again, we can use small angles, so that theta for that is 3 centimeters over 250 kilometers. And that, now what that should, these two angles should be equal. If you're right at the minimum, this is the requirement for the minimum, so I can take this and set it equal to this other angle. And then it's actually your home free. You can, we do need to know the wavelength. He didn't specify that here. You'd maybe want to go up and ask him. I assumed it was kind of in the middle of the visible spectrum, just so I could come up with a number. You probably would want to ask him on that. Maybe he'll let you use whatever wavelength you want. But we can go ahead and do that, and we get a diameter of this either lens or mirror or whatever that opening is of 5.6 meters. And then we could be able to resolve that as an image. And it would be blurry, but maybe just discernible. Okay, so so these are typical of exam questions, though. So I would be ready to do these. Okay, there's just one other topic we haven't gotten to yet. This is kind of a fun one, the idea of polarization of light. The idea that light is coming, it starts off, we say, unpolarized. Light is a transverse wave, it's vibrational. If it's coming at you, it can be vibrating in any number of different directions coming out, as far as the transverse nature of it. We're going to represent unpolarized light that way. This is kind of a 3D look. I'm just going to draw it like this, unpolarized light vibrating. Again, picture this is coming straight out at you, or we're going to put some filters over it to see what happens. From this, because of the electric field is a vector field, we can take these vectors and we can break them into components. I can break them into components in the x and also in the y direction. So I'm going to add up, if I break these up into separate components, I'm going to add up E in the x and add up E in the y. If it's truly unpolarized, these are going to be identical. So I've got two of these. And so this is just the equivalent of unpolarized light. Then if I take my first polar filter, this polar filter I'm going to put on top of this thing, and it's got what's called a transmission axis along one direction of it. We need to kind of know what that is. And if I put that on top of this, this will allow transmission of the light that's vertical, but this stuff that's horizontal is going to get blocked. So this first filter is just going to take and give me from unpolarized light, is going to give me some polarized light as it emerges from it. And it's going to turn out that it's really just half the light, you could say. So immediately that initial intensity, which is going to be proportional to the square of the electric field, should be, for this first one, I'm going to call that I naught, I1. That'd be the intensity coming out of this first filter is 1/2 I naught was the original intensity of the light that we had. So first filter polarizes, but yeah, it's, okay, that's basically it's going to emerge polarized light. Now what I can do is take another filter and put it on top of this one, maybe with a different polarization axis. In fact, I've got this drawn here. So this E1 that gets through this first filter, which would be half the light, is going to get through here. And if I put this other filter with its transmission axis this way, we can rotate this. Now, I can take this and get components to E1. And those components for this and this are going to be along this line. And so this is what's going to emerge from this filter. So I can look at, this is going to be E2, the electric field coming out of this one, is going to be equal to E1 times the cosine of theta. And that would be the angle between the polarization and the axis. E1, I've already, so we've got this. And then what I'm going to do is, the intensity is proportional to the square of the electric field, so I'm going to end up having to square this. This is going to be E2 squared, is going to be I2. Squaring E1 is going to be I1, which was really just 1/2 of I naught. What we have to be careful, we're going to square the cosine, and that's that angle between the transmission axis and the polarized light. And so that is that second intensity coming from that filter. Something you want to keep in mind, though, that we start off with polarized light that's vertical. When it passes through this filter, the filter didn't just kind of leak. It actually, what emerges is a new direction to the electric field, and it's lying in this direction. And again, it's just the components along that axis. Any components that are perpendicular to that get absorbed, so they're not going to get through. So this is the basic idea. You can set up any number of changes. I can come up with another filter and come over here with respect to this one. So I could have a theta 1 and a theta 2, and you can get a long chain of these terms as you develop it. So that's the basics of polarization. And I don't have an exam question for you on it, although he certainly has used it. These are typical test type questions.
One more question.
Yeah.
So what confuses me is the light's vertical E1, but then there's no X components that go through the second film that would turn it sideways.
Oh.
Because there's nothing in the X that would pass.
Oh, right. So, okay, you can't do it with one filter. So, I mean, 2 filters, it blocks it, right?
Yeah.
A third filter, you can make it go as long as that third filter is between the other 2. When we come out of this one, the electric field is changed in direction. So now if I took a third filter and its polarization axis was like that, where then this does have a component in that direction. So if we do that one more time, we can get transmission taking place. So it doesn't get through 2, but it gets through 3.
Okay, so right now with the light getting through
it could get through. I could have another filter here that's polarized this way. This has got a component that's in this direction, and the math will work out and tell you the amount that gets out of there. But yeah, that's a mind-blowing thing. But that does also emphasize that it does change direction from here. So even though we started off, we just picked off the vertical, this one, we do get some coming out this other angle. Okay. Wow, got a lot of stuff, but we didn't come out too bad with time. But okay, I'm realizing I'm just cramming through this stuff. I hope it goes well for you. And we'll see you on the other side.